Good morning, and welcome to this session on distributed deep learning using Java on the client and in the cloud. So this is actually a mix of a number of topics. We talk about deep learning, we talk about Java, we talk about mobile client development, and we talk about cloud development. It's pretty complex, I realize that, but I think it's important for many people, software developers and integrators to have a look at the whole picture. I'm not going into detail too much on the different aspects, but I'm open to questions, of course. So just for my understanding, there are, when you talk about AI software development, some people categorize themselves as data scientists and others as software developers. So while I think that's not entirely correct, but who here considers themselves rather as a data scientist? And who is more a software developer? Okay, that's interesting. So that means that that we will need a quick introduction into deep learning. So what we will talk about today is, first of all, what is deep learning and why is it important, and it's a very hot topic these days. How can you use Java and Java on Oracle Cloud in order to get to high-performance deep learning? How does that then apply to client-side deep learning? Why do we need deep learning and AI on the client? And how can that then still improve the general model, the neural network in the cloud? And we will show how you can leverage the Java deep learning algorithms and create cross-platform applications for mobile applications written in Java. And you can run them on iOS and Android. So deep learning is a specific class of algorithms that are subclasses of machine learning in general. You can have supervised and unsupervised deep learning. In supervised deep learning, you supply a data set and you also supply the result, the classification. For example, this is a dog, this is a cat. In unsupervised learning, the model will learn patterns. Typically, you provide raw input data to such a neural network. It can be images, text, numbers. If you supply an image, the image is, of course, digitized. So in the end, you always supply numbers. Those input data traverse a number of layers, and the last layer is typically a classification. So this is how it can be easily visualized. We have an input layer, and then one hidden layer and an output layer. In many classification algorithms, you have a larger amount of hidden layers. The analogy of deep learning comes from how the brain is working, how the human brain is working. Neurons in the human brain can be looked at the nodes that we have there in the image. And information and processes in the brain transfer from one neuron to another neuron. And sometimes the information is increased and sometimes it's decreased. And that is how information flows in our brains, and that's how information flows in a deep learning network. When the input is given to the first layer, then there are some weights that will determine how that input is then propagated to the next layer. There are some basic mathematical computations that are being performed, and in the end, so that process traverses layer by layer, and in the end it will result in a classification. For example, in this is a cat. So that is extremely briefly how deep learning works. If you want to know more about it, during my presentation I have links at the bottom where you can learn more about deep learning itself. So if there are questions about deep learning, feel free to ask. Interrupt me when things are not clear. And otherwise, feel free to take a note on where you can learn more about specific things. So deep learning and actually many data science applications in general are often written not in Java, but in Python, in R, or in specific DSLs, MATLAB, for example. And one of the ideas that that I sort of stole from James Governor from Redmonk is when web shops grow up, they become Java shops. So what we see in many web-based applications in big web companies, they start with PHP or Node or something like that for doing a prototype. And then when they need to scale things and when they need to be performant and have multi-threaded support, and so then they turn into Java. And I think actually for science this is more or less the same, because data scientists, they use Python or R because it's very easy to quickly read a file, analyze it, plot a graph. But you can also do that in Java. And there are a number of initiatives that are doing that in Java. And why do I think it's important to do this in Java? Well, first of all, we love the Java language, of course. But second, once these algorithms are more or less ready, and they can become integrated in a product, because an AI algorithm hopefully never lives alone. It should always be used in applications. Amazon's book recommendation, for example, is used in real-world applications. And once you want to do that, you have to think about things like scaling, security, locking, accessibility, availability, localization, all these enterprise things that Java is excellent in. So therefore, sooner or later, you have to move your scientific prototype to a programming language that's more suited for the cloud. And there is a framework called Deep Learning for J. It's created by SkyMind, which is a company focusing on neural networks and deep learning. And it's completely open source, and it provides Java APIs for doing deep learning algorithms. If you think about Java APIs, that it might be slower, that is not the case, because the Deep Learning for J implementations, they depend on some specific libraries that access the native mathematical libraries of the operating system, OpenBLAS, for example. And also they leverage the GPU as much as possible. So if you execute some Deep Learning for J application on a system with a supported GPU, it will leverage that GPU. So it's really a first-class platform for doing deep learning. And it is open source. So it is there's no vendor lock. You can easily get the source code. The hello world of deep learning is MNIST. Who here heard about MNIST before? Okay, a couple of people. MNIST is a data set containing 60,000 labeled images and then 10,000 other images. The images look more or less like this, although there's some pre-processing done on it already. It is a typical example of supervised learning, because those 60,000 images, they are handwritten digits by different people who wrote a digit and then labeled it. For example, the top left corner is a tree. And that's easy to recognize, but for example, the third row, that's already much more difficult to recognize. But this MNIST dataset can be used by deep learning algorithms to train themselves, because we give those 60,000 digits to the algorithm, and we tell, hey, now try to predict for each digit which number this is. If we would go back to our slide where we showed the general prototype, MNIST ends with 10 output layers. With one output layer with 10 digits in there. And the input layer is a 28 by 28 matrix that flattened into a vector, and that's sent through the network. And in the end, we want to get one of those output layer nodes to be 1, and all the others, we want them to be 0. And that is what the algorithms are doing. They will adjust the weights that we talked about. They will adjust the biases. They will work with some activation filters in order to try the best possible weights that will then fit the 60,000 images. And in order to test it later, you have the 10,000 labeled images that are then done to see how well your algorithm is performing. So that is something that we will use in this session today as well. The code that I show in this session is freely available on GitHub as well. It changes very often because we are making changes, and we're very fortunate to have some of the Deep Learning for J committers contributing to this code as well. And to make it easy to get started, the code contains a Java standalone application that will train the model and that will make predictions. So prediction is, once we have we trained the model, we give it a real image and we ask, what do you think? Which digit is this? That is the standalone application, and I think that's good for if you want to do some local development. If you want to do this in a server environment, we can. The code has a project server, and that is using a Payara Java EE application server running on the Oracle Cloud. It's running on the Oracle Bare Metal Cloud, so the classic instance. And the third part of the code is a mobile application, and that mobile application is sending requests to the cloud, and it asks, what do you think this is? And it is then, the cloud is making a prediction and is sending it back to the mobile application. So the first part, the logic part, is required to train and evaluate the network. So the code retrieves the 70,000 labeled images. 60,000 of them are used for training, and once the algorithm thinks, yes, now I'm pretty okay, the test data is run in order to see how good it actually is. The quality can be measured by seeing how much of the test data really fits the labels, because all test data comes with a label. It's this is a tree, and then the label is tree as well. So that allows you to test how good the model is. In the GitHub sample, we supplied a few ohm digits that are not used for training and testing, and that can be used to predict how good the thing is working in real world. So again, I'm not going into detail about the deep learning, but this is a snippet from the code. This is how we create a neural network. So we use a builder pattern, and we tell its optimization strategy. Once you learn something about deep learning, you will recognize terms like stochastic gradient descent. And so that is a technique that is used to improve the model based on backwards propagation. So when the outcome of a model is not good, the parameters will be changed in order that it becomes better. And the way that the parameters are changed is a scientific topic by itself. As I said, we have two layers here. So first of all, the input layer, which has height times weight input pixels. In the case of MNIST, this is 28 by 28, and it will have 100 output nodes. So the second layer, the hidden layer, has 100 nodes, and that layer, which we described in layer 1, has 100 input nodes, and it has output num output nodes, and output num is 10. So I actually should have written 10 here, but you never know if you want to do this for characters as well. Question?
Yeah, I didn't quite catch it. What exactly do you put in the input layer in this example? Is it just 5 or 4 different 9s or 4 different 3s?
So the question is, what do we put in the input layer? The input layer contains, so we start with an image with 28 by 28 pixels. Each pixel has an RGB value. We first translate that to gray values, and then we translate that to values between 0 and 1. So each number, each float, each double that is used as an input here is a number between 0 and 1 that corresponds with the gray value of a specific pixel in the picture.
So each input would be a different pixel?
Exactly, each input is a different pixel. And that is then how the algorithm works. If the pixel, and we don't know how it works internally, but it might try to get some features about pixels that are vertical might lead to this number or whatever. But we give it meaningful input, at least meaningful to the algorithm. Pixels but we have to do some pre-processing, and that's why we scale them to values between 0 and 1. There's actually, sorry, there's actually on the deep learning for JWeb a great tutorial about MNIST, and they talk in much more detail how it works. More questions? Okay. Sorry. The second layer has 10 output nodes, which we said is digit 0 till 9. And we hope that the correct output node will light up, so that that will become 1. For example, if we have, if the 6th node becomes 1, then we know that the model thinks that this is digit number 5, because we start with 0, of course. We set back propagation to true, which allows to retrain in an efficient way. And yeah, that's the most important part for the creating the neural network. We trained it, and then we ran the test data on it. And this is the what I call the confusion matrix. So you can see that if we provide a null, then in most cases the algorithm thinks this is a null indeed. So there are some edge cases where a null is provided, and the algorithm thinks it is a 6. So in 11 cases there was a misprojection. I think it more or less makes sense, because a 0 and a 6 are slightly related or slightly similar. So therefore it makes sense that that these miscalculations happen. In many cases it's also not trivial, because my son, for example, when he writes a 6, in most cases I think it's a 0. And so even the best algorithm won't be able to fix that resolution between us. So far that was for deep learning. I mean, that was the shortest introduction ever in deep learning, but I hope that you basically got the idea. In the end, it's mainly about matrix operations. So it's performing linear algebra, and you can do that in Java, and it will be very fast. But how do you use that now in real-world applications? Most deep learning applications somehow need the cloud setup, because they are only effective if they're used with lots of data. And when we think about lots of data, we think about clouds. So those algorithms need to run on cloud systems as well. And our Java code, the snippet that you saw there, comes from a Java application, and it's very simple. And if you have the Oracle Cloud, you can create by now you should know that you can get a, I think, $500 credit, free credit access on the Oracle Cloud. The easiest thing that you can do there is just set up a Compute Classic instance with Java on it, and download the sample application and run it. Because then you will have the deep learning algorithms running on the Oracle Cloud. So the server application, which is a part of the open source GitHub project as well, it is using a Payara Micro, which is the microservices edition of the Payara application server. Who here is familiar with Java enterprise development in general? Okay. Sorry. And all functionality is available via REST services, which is one of the most common ways to do this. When I talk functionality, this is, for example, make a prediction on this image, or give me the model, for example. So that is functionality that the server application exposes to clients that will ask it. So this is a very simple handler. So it's using a JAX to tell that requests that are prefixed with the path handler and then have the path classify image, they will be handled by this method. We will send the JSON string back. And what we will do is, oh yeah, you see that we give raw data as byte. This is data of the image, and it can be a big image because the code in the Java layer will translate it to 28 by 28, will put it to grayscale, and then translate it between 0 and 1. So that is what our simple application asks as input. Note that what we will talk about later, but we typically want to have some header parameter in our handlers as well, because you don't want the whole world to access your application. So you want to have some security, which is very easy with Java on enterprise frameworks. I'm using Java EE, but you can do that in Spring or any other Java framework as well. So again, that would be a whole topic by itself, how you have to create a server application for deep learning. And again, I'm not going to touch this because I think it is very important that you get the broader picture before you decide to dive in the different areas. So what we do when we get the bytes, we will ask a service which is injected, which is the model service, which is part of the Java specific application that I showed a snippet from. And there's a method predict, which takes bytes and which will give an ND array, which is actually, in this case, it is a 1 by 10 matrix with the 10 labels. So it will give the prediction, how likely is it that the number that you gave was a 0, how likely is it that it was a 1, a 2, a 3. So ideally, you want this number to be, you want this matrix to be, for example, 0, 0, 1, 0, 0, 0, 0. Because then we know that the algorithm is completely sure that this is digit number 2 or 1, I lost count. In practice, it will not be that black and white. It will be, but what we see with good digits is that you have 95% chance that this is a 6, for example. So that is what the server application returns. Then the mobile client, and this is also something that might be better suited for a whole session, but we will briefly discuss it and show links to more details. We use a Java application as a mobile client. So who in the audience was aware that you can use Java applications and run them on iOS and Android? Okay, it's improving. It used to be much smaller. So with this application, and I won't have time for switching back and forth between demos and so, but what you see here, and actually I tweeted about it, but what you see here and what you see here is the same Java application, that 100% the same Java code, and it runs on desktop, on iPad, and on Android, and on embedded as well. So again, this is a huge advantage for Java developers. If you written that server, or if you took that server and the client and the logic code, you can use your Java skills to create mobile apps. While I'm here, it has the button with Cloud Predict, and it will then send a request to the cloud. And the ones in the front row can see that there's now, can someone see it? This is 6, it mentions. I have a witness. Yeah, so it mentions this is 6, and this is not hard-coded. This is now really going to the Oracle Cloud, and it was sending the bytes that we were, well, of the image. So we're using Java to create the logic on the client, and JavaFX to create the user interface. With JavaFX, it's cross-platform from the first minute. So because JavaFX is the client framework for Java, which allows you to create modern UIs, and then they run the same on Windows, Mac, Linux, but also on iOS and Android. If you want, you can use specific styles for having different styles sheets on iOS and Android and so. But what we see is that most companies prefer to have it branded in their brand rather than in the specific iOS or Android brands. But anyway, I think this is not HTML being rendered. This is really the JavaFX controls which are rendered on top of the GPU using OpenGL. So this is near native performance and look and feel, I think. So what we do on the client is we send the image to the cloud. Okay, so this is important. We send the image to the cloud. I will come back to that later. The cloud will will calculate a prediction and will send that back to the app. And if the result was incorrect, the app asks, is it incorrect or correct? Now, this is not, of course, something that you will do in a real-world application, but the same principle is done, but more subtle. For example, you will get a book recommendation, and then the algorithm will ask you, did you like this recommendation? And then you say yes or no. And if you say no, they might even ask why not. And that is actually how those algorithms are trained. So by asking users, was this good? Was this what you want? If no, give me some feedback. And that is how the algorithms become, or the result of the algorithms become better and better. So very briefly about Java on iOS. So you can use Java 8 applications. We're working on Java 9. It's beta on iOS. So you use Java FX 8. Tooling is very important. We focus a lot on the IDE plugins. So if you use NetBeans, Eclipse, or IntelliJ, there's a Gluon plugin that will make sure that if you install that plugin and you write your Java code, then your project will have additional tasks to deploy it on Android and iOS as well. Unfortunately, at this moment, if you want to deploy on an iOS device, you need a Mac, because there are some Mac internal tools are used. We have a library called Glisten, which makes sure that your application looks shiny and mobile. And there are APIs for doing communications and also connections with native systems. So, with native device capabilities like GPS, camera, and so camera is of course important in these kinds of applications. So, sending data from the client to the server, as I said, it uses authentication, or it is recommended to use authentication. It is not recommended to open the REST points on the server to the whole world, especially not if you're going to do mobile development. And many of the deep learning applications, or AI in general, will start from mobile applications because that's what users are increasingly using. But imagine if all those mobile applications are accessing your backend application. That would be a huge security risk. Especially, what if all of a sudden there's a problem in your mobile application, and you can immediately patch it, but if it was a website, you could immediately patch the website and everyone would use a new website. But with a mobile application, you never know when users are going to update. So they might still be using the old insecure application. So therefore, it is always recommended to not use direct communications between mobile apps and sensitive servers, and not expose the endpoint to the public world. And that is where, with the Gluon tools, we have something called a remote function. And a remote function is a client-side object that will send a request to middleware. Our middleware is Gluon Cloud Link, but there are other systems that do something similar. And there, on that middleware, the request is mapped to a REST endpoint. And in this case, the REST endpoint is on the Oracle Cloud. If you want to know more about this principle, the link below will explain you all the advantages and why and how you have to do this. And we won't go into detail there, but if you combine then everything, the architecture looks more or less like this. So we have a mobile application, and we have a backend application running on the OCI, or the bare metal cloud. The mobile application is talking to middleware, Gluon Cloud Link, which is this middleware for allowing data synchronization, storage, and flexibility, and synchronization, and security and configuration, can be installed on Oracle Cloud. We have Gluon Cloud Link running as a SaaS solution, where it runs on AWS, but you can also use the Oracle Application Container Cloud to have that middleware specifically installed in your environment. And doing so, you're completely safe. At least, well, you don't share resources with other customers and so. And there, the Oracle Cloud provides a handy way to distribute software applications like Gluon Cloud Link. We have an installer for that. The result is that the middleware is on the Oracle Cloud as well. You can manage it via a web interface, gluon.io. And requests coming from the mobile application go through Oracle Cloud and go to the backend application, which is in this case also running on the Oracle Cloud. How does it work in the code? So when we want to classify an image, so we have an image and we want to get a prediction, we are not opening a REST connection to that server that we showed. We could do, but we will not be able to properly authenticate because we don't have the credentials. You should not put credentials in a mobile app. You put those at Gluon CloudLink, for example, and CloudLink will see this request and will then call the application with the correct credentials. So what we do on the client is we have this byte array, it should be small bytes. That's a pity with PowerPoint, it always tries to capitalize my declarations. And we create a remote function. The remote function is named classify image. We provided the body, the bytes of the image, and we say that we want an object back, not a list, because you can get lists as well, and it should be then transformed into a string. And when we call the get on the observable object, we will get the result, which is the result from the prediction. I have one screenshot here on how that looks. I can quickly show it. So this is the operation tool for Gluon CloudLink, where you see we have so it's running at gluon.io. We have a function named classify image, and that is what the client knows. And it is configured here to go to, and this is the URL at the Oracle Cloud, and it will go to server handler classify image. If you remember the path that we showed in the beginning, that is exactly this path. And we can check the caller for seeing who called us and when. And for example, if there was an error, we can investigate the error. And for example, connection refused. That was because the cloud instance was not running at that moment. So this is how you, and then authentication. We can provide different authentication algorithms, and we can configure our remote function to use a specific authentication method that we provided. We can set more things like timeout and so on. So again, not going into detail for this one, but it is important if you want to do real life applications that are using deep learning between mobile and cloud. Okay, and now actually the most important part of the presentation. I said in the beginning, I said 11 minutes ago, I think, we're sending the image from the client to the server. But we didn't ask permission for this. So we are in post-GDPR era now. So we have to be careful about privacy. And we're getting much more questions about this, because we were now sending the simple 6 image, which is here, and which doesn't say much about me nor about the audience. Actually, when I was thinking about how to do this presentation, but it would be too complex, I would actually ask someone in the audience to draw on a white paper a digit. I could then take a picture and then send it to the cloud. And then you could all sue me because you didn't give me permission to put pictures of you and send it to the Oracle Cloud. And that is something that's increasingly getting important. People are less and less comfortable with information being sent to cloud systems, even though it's not, it's hard to explain that to well, you know, if you're at a family party and there's always an uncle that complains because he thinks that at Facebook there are people, hey, now you have to look what he wrote. Well, let's correct this. And so it's not that human beings at those companies are reading or watching what you're doing, but still, so it's algorithms. I'm not even sure what makes me most uncomfortable. So whether you like it or not, and whether you want to give your data or not, you have to take into account that not everyone will be willing to send his data to cloud systems. So what do you do in that case? Well, Another example is self-driving cars, autonomous cars. They often send scenery or they send pictures and video footages to the cloud systems. But that actually means that, and you give permission for that, that actually means that people over there in the cloud know where you have been and what you're doing. So that might become scary. So the solution for this is distributed deep learning. And now this is actually the main reason why we are using Java on the client, because with the Java algorithms and with the deep learning for J algorithms, we can run predictions locally on the device as well. And we can use the same APIs that we use on the server, but then on the client. And doing the classification is actually very, very fast. If I click on local predict, you will immediately see a result as well. So that is a very fast calculation. Now, what did we have to do for this? The model is still retrieved from the server, but the model is just the weights that the algorithm is using to make predictions. There's no, it's close to impossible to trace that back to individual data. It is actually impossible. But the predictions, so the model comes from the server, but the predictions are made on the client. So the raw data is never leaving the client. And that is a big advantage, because the security problem is solved by this, because we don't have to ask a user permission. Do you want, do you allow this app to get your video and camera and send it to the cloud? That won't be needed anymore, because the data is not leaving the cloud. So how is that going? Again, a snippet from the repository. It's using all deep learning for J code. We have a native image loader that does the pre-processing, that scales it between 0 and 1 values. And then at the bottom we have model.predict row, and that will give the predictions in order of likelihood. So it will first say 7, 6, 3, for example. And our answer, what we guess, is what's being predicted there. Again, this is deep learning for J APIs, Java APIs, the same as on the client and the server. The reason that they are, actually I was surprised to see the performance on iOS. And the reason is that the Java code calls native code, and Apple has with Accelerate library a pretty good fast mathematical library. And you can use OpenBlast as well, which is also a decent fast library. There's one drawback though, well, probably more, but we can't learn easily. If I was saying about, if I was giving the example about the book recommendation, and then the website or the client asks you, did you like it? And you say yes or no, so you give input back. If everything happens on the client, you can't give input back. Well, that is still possible, because we can do local retraining on the client. We can retrain the model on the client, because if the image was wrongly predicted, and if I click on incorrect and I specify what it had to be, then the model can retrain itself, more or less similar than how it would be retrained on the cloud. But there on the cloud, of course, it will have millions of input, and on the client, it has only one new additional input. So you need somehow different algorithms, and you also don't need to send the whole model, but that is in an increasingly important topic that's being discussed, and that is distributed deep learning. So you see, we get the model from the cloud to the client. We make some predictions, and we make some adjustments to the model, and then we send the gradient of the model back to the cloud. And because we are sending the gradient of a model, so a derivative of our data, it is, or you can at least make sure that it cannot be back traced to your original image. So with this technique, client-side learning, you send the information back to the cloud, but not in a raw way. So you're not sending the picture back. You're only sending, hey, if you, I had a picture. I'm not going to tell you what it was, but you thought it was a 5, but it should have been a 6. And by adjusting some of the parameters like this, it worked much better. So here are my, it's actually a Git diff that you do. Yes, question? Am I sending back pixel properties? No pixels at all, no. So the only thing that we are sending back are the weights of the model, and not the original pixels. We use the original pixels to retrain the model. And by using these pixels to retrain the model becomes better. And then we can tell the cloud, hey, your model was pretty okay, but it failed in some way, and I improved it. Here is my improvement. And if many clients do that, if many clients send small improvements, the model on the server can learn. So this is, again, a code snippet that you can find in the sample. This is how the client, we create a new array with the labels, and we, if label is, for example, 6, we will make sure that the 6th element, 0, is 1 in our results, and we call then model.fit row, which is the raw data, comma labels, which is the our trained result. So we provide the pixels, so row can still be traced to the pixels. We provide that to the model, and then the model fit will make sure that it will retrain and make sure that would be matched correctly. And then we call the gradient of that model, so what has changed, and we send that, again using a remote function, back to our cloud instance, using the publish gradient, where we send again a byte array, but that byte array cannot be reverse engineered to the original pixels.
Excuse me, I have a question.
Sure.
How can you be sure that new values of weight will not decrease the performance of the overall model?
Yeah, that is excellent. Because you might some local people who want to trick the system, so they will give false information. Therefore, we have a server-side update as well, and very short, we get the new gradient, and we want to compare it with our gradient. And you can. The most silly thing is that you just take the average of what you had and what the client had. But what is better is that, and this is a code snippet from a sample of deep learning, is that you do much more complex applications. You also compare it with what other people were sending, and then you will the false positives or the data that is completely off will be easily detected. And you can go even further, because you can then label that data coming from this user or IP address is bogus. So that might be on purpose that he did that. But actually, I'm very happy with the questions here, because those are very, very relevant questions. Yes, question there.
How can you control the limitation of the number of the local device? If the client want to send many data, want to chain it in the local device, how can you control it?
How can you control the load on the client, you mean? So if the client has 1,000 predictions and it can't process that locally anymore, that is what is typically done, is that the model retraining is not done during you using the application, but it's done at night, for example, and it is offloaded to a moment that because even if it goes pretty fast, it works best if it uses the GPU, but the GPU is also used for rendering. So therefore, you typically wait till the phone is not used anymore, and then there's no specific code for this yet. So that is something that you indeed have to write carefully. If it's just like this, you have one digit. The retraining takes only a few seconds or so. But if it takes longer, you can play with the parameters of the model. You can determine how many iterations and that way you can control how long it will take. Question over there? Yeah, performance is more or less similar, because they all use the same OpenBLAS implementations in the native layer. So it's very similar. We're actually using OpenCV, because for scaling the image from full-blown to 2828, we use OpenCV. I can actually, if you look at in the sample at the dependencies that we're using, there's a great project called Java CPP, and that provides Java entry points to native functionality. OpenCV is one of them. OpenBLAS is another one, and so that gives us access to this at the same speed. Now, going forward, there's also there have been talks about the vector API in Java that might then combined with AOT might be extremely performant as well. But for now, the Java CPP, where we match the Java APIs with the native implementations, is its native performance. So that is and it's in Java, so it's cross-platform. So but it is and it's the same principles that TensorFlow is using as well. So trying to combine the good things. So running out of time. So the conclusions is that with deep learning, there are many opportunities. Now, don't overhype it. It still goes wrong very often, and it takes lots of good data, lots of clever people to come up with the best algorithm. But Java developers can use those deep learning APIs, so there's no reason to wait. There's a deep learning for J, and you can run the basic samples and integrate them with your enterprise applications. You can run them on the Oracle Cloud or any enterprise framework, any cloud system that you're familiar with. And you can also run them on mobile with Java mobile applications. And you can leverage the power of the mobile device to guarantee the privacy of your users by doing not sending the raw data. Increase the security by not calling an endpoint directly, and still improve the cloud model by sending the information back to the cloud. So that's in a nutshell some end-to-end deep learning Java mobile, Java cloud. If there are any questions, my email address is there, so don't hesitate to ask. Or if there are any questions now, I think we have -4 minutes for one question. Yes, one question there.
When we talked before about updating devices if model was removed, on operating systems like iOS, how does that actually work? 'Cause I thought the background was quite restricted on those OS.
Can you repeat the first part of the question?
Sorry, so when it comes to, when we talked before, updating the model overnight, how can you do that on iOS?
Yes, yeah. Yes, yeah. Well, with one of the libraries that we have in Gluon Mobile, you can send notifications. For example, notify me in at 2 a.m. and then the application will get notified by the operating system and will be allowed to do something. So that is an OS specific thing that we abstracted in a Java API, and same for Android. Okay, the next presentation is already there, so we are. I'm still open for questions. Those are my contact details. Thank you.